In this video, you will learn how to derive the period of a simple pendulum, using the law of conservation of energy and integration. Let us consider a pendulum, which is oscillating between the angular displacements, θ0 and negative θ0 from the vertical. θ0 is called the amplitude of the pendulum. First, we are going to find the total energy of the pendulum. The pendulum consists of a string and a weight, called bob. We assume that the string has negligible mass, so it does not contribute to the energy of the pendulum. So the total energy of the pendulum is the sum of the kinetic energy of the bob and its potential energy. Kinetic energy is 1 over 2 mv squared, where m is the mass of the bob, and v is the magnitude of velocity or the speed of the bob. And the potential energy is mgh, where h is the height of the bob from a reference. Put the reference line at the lowest point. At this position, the height of the bob is h. The angular displacement of the pendulum is theta. Let L is the length of the pendulum, which is measured from the point of support to the center of the bob. So this length is also L. Let this height from here to here be y. So the height h is equal to L minus y. Now in this right triangle, y is the adjacent side to this angle. So y is equal to L times cosine theta. Substitute this for y. Now factor out the L. We are going to find the period of the pendulum for smaller angles. That is, theta is less than 15 degrees. For smaller angles, 1 minus cosine theta is approximately equal to theta squared divided by 2. Now substitute this for 1 minus cosine theta. And substitute this for this h. Add the two energies, you will get the total energy. The pendulum stops at the extreme positions before continuing the motion. So when the angle theta is equal to the θ0, or negative θ0, the velocity of the bob is 0. Substitute 0 for v, and θ0 for theta, you get another equation for the total energy. Equating these two equations, you get this equation. All the terms have m, so you can divide that out. And all the terms are divided by 2. So you can cancel out the 2's. Now move this term to the right-hand side, and isolate v squared. And factor out gl. From this equation, v is equal to square root of this. V is the velocity of the bob, which is a linear velocity. The linear velocity is related to the angular velocity omega by this equation. R is the radius of the circle, which is equal to L. Angular velocity is equal to the rate of change of the angular displacement theta. Substitute this for omega. Next substitute this for v. Now divide both sides by L, you get this equation. I have separated the square root of g over L. Now take the reciprocal of the left-hand side and the right-hand side. Next solve this equation for dt by multiplying d theta, both sides. To find the period of the pendulum, we need to integrate dt. The period of the pendulum is the time it takes to go from here to here and come back here. So the period is twice the times it takes to go from here to here. At this position, the angular displacement of the pendulum is negative θ0. And at this position, the angular displacement is θ0. So multiply a 2, and integrate dt, from negative θ0 to positive θ0. Substitute dt from this equation. I have put the constant factor outside the integral. To evaluate this integral, I am going to use this formula. Integral dx over square root of a squared minus x squared is equal to sine inverse of x over a, plus a constant. So t is equal to 2 square root of L over g, sine inverse, theta over θ0. Ignore the constant as we are dealing with a definite integral. Put the limits. Is equal to 2 square root of L over g. Sine inverse. Substitute θ0 for theta. You get 1. Minus. Sine inverse. Substitute negative θ0 for theta, you get negative 1. Sine inverse 1 is pi over 2. Sine inverse -1 is negative pi over 2. Pi over 2 minus negative pi over 2 is pi. So the period, t, is equal to 2 pi, square root of L over G. If you learned something from this video, and want more videos like this, I ask you to subscribe to this channel. Thank you.